So we've talked about double integrals over rectangular regions. So now let's go ahead and talk about double integrals over general regions. So there's going to be times where you don't necessarily have to have the limits of integration be just numbers. So sometimes you might want to find the volume, but underneath a much more general region. So let's say you have this surface up here. Okay, this function f of x comma y, and maybe you don't want just a regular, I don't know, a regular rectangle from 0 to 1. Maybe there is like some sort of curve here that you might want to find the area. Okay, so something that looks like that, okay, in the xy plane. So what you can do is you can project this guy up here, right? And that will just give you the volume of this particular region. This looks so ugly, okay? Okay, so let me go ahead and attempt to draw it again. So maybe it looks maybe something like that. Okay, so you're looking at that particular volume. So you can look at a volume that looks not like a rectangle, but it can look like something weird. So that's just going to depend on what the x and y coordinates are going to be like. So there's going to be some sort of equation in the x and y plane that you're going to have to project up to the z, up to that particular function of two variables. So that's why we have the double integrals over general regions. All right, so what do they look like? So you're usually going to have two different types of cases. So the first case is case 1, where you have y as a function of x. So here you can see that you have y is equal to f of x. This is something that you might have seen in Calc 2, where you have the upper region over the lower region. Okay, it's kind of like the upper minus lower. So this is case 1. You might have a function of two different curves, and they're both functions of x. You can also have case 2, where maybe you have some sort of conic. So here you have x as a function of y. Okay, so you have something a little bit different. Okay, so in this case, remember that where this one was the upper minus the lower, in this case it would have been the left or the right minus the left. Okay, so you have two different cases, and it'll really just depend on what you want to do. Typically, you can make any sort of general region into any case that you want, but there's always going to be one that's always easiest than the other. So we'll go ahead and take a look at what that looks like. So here I have a little notation. So let's say, for example, you have case 1. So in this case, the way that you're going to set the double integral, it's always the following way. So the inner integral is always going to have the value, the functions themselves. So the way that I like to think about it is that I like to draw an arrow from the x-axis all the way up. So the first graph that this arrow hits is going to be my lower limit of integration. So you see how this guy hit the g of 1 of x? That's why g of 1 of x is on the bottom part. And the one that where this arrow comes out of, that's going to be the upper graph. Okay, that's going to be the upper limit, the g2 of x. That's why we have this g1 of x, g2 of x. Now, because these guys are the y value, since the arrow is going upward, kind of like in the direction of the y value, the inner differential should be dy. Okay, now this is going to take care of this particular region. So I already took care of this weird mess, this weird region. Now the outer region has to be the values of x, the things that are left over. So though these guys are always going to be the numbers. So whatever's on the outer integral should always be the value. So in this case, since we're looking at x's now, since we already took care of the y's, it's going to be wherever I want, you know, this region to project up to the f of x comma y. So sometimes there might be bounded regions where you might have to solve for the values of x. Sometimes they might tell you that it's between this value and this value. It really will just depend, but that one's always going to be the outer. Now, same thing with this guy, case 2. So now if something was given to you in case 2, because I'm looking at the x values, okay, x is a function of y, I like to draw an arrow going from the left to the right. going this way. So the graph that it hits first, which is typically the left one, is going to go on the bottom limit of integration. That's h of 1. That was the blue one. That's what this one's called. And then where it kind of sticks out, where the arrow comes out of, that's going to be my upper limit of integration, the h2. Notice that this arrow is going in the direction of the x-axis, which means that the inner integral should be dx. All right. And now what would be my leftover? So these guys, putting the functions there will take care of this shape. All we just need to let the integral know is that, okay, my leftover dy is just going to be where these two graphs meet, or maybe the two y values where you want to be able to find the volume of. Okay, so that's where the outer integral will be at. Okay, so again, one way to kind of really know is which case do you have and which one would be easiest for you to work with. So if you can make it in case 1, a lot of students really love case 1, but sometimes there will be problems where you cannot do it and you might have to do case 2. Sometimes it will just depend on the function itself, where if the function gets really, really complex, maybe one case is better than the other one. All in all, you really just have to try them out and see what would really help for yourself, and then go based on that. So let's go ahead and do an example. So let's consider the region in the first quadrant between y equals square root of x and y equals x cubed, and describe the region as both a type 1 and type 2. All right, so let's go ahead and take a look at these two graphs. So I'm going to look at y equals x square root of x and y equals x cubed. All right, so that's going to look like the following. And we're looking at just the first quadrant. So the square root of x, we know that that guy kind of looks like an eyebrow, kind of like that. And we know y equals x cubed kind of looks like a piece of spaghetti, kind of like this, right? And these two, because they're parent functions, they're going to intersect at 1. At 1, 1. And notice that they also intersect at 0. Okay? Now, also, in case you just don't know, like if you're like, wait, how did you get 0 and how did you get 1? The easiest way to kind of figure out which one goes with what is just by setting them equal to each other. If we set these two guys equal to each other, you get square root of x equals x cubed. I can square both sides. You get x is equal to x to the 6th power. Oh gosh, I almost didn't know that. X to the 6th power. I can minus the x over, so you get x to the 6 minus x equals 0. Factor an x out, x to the 5th power minus 1 equals 0, and there's where you get x equals 0 and x equals 1. So you can still do it algebraically. Okay, one thing that you should never do is at least, one thing that you should never do, is divide by the x, because then that's how you lose that 0. All right, so now let's go ahead and describe it as a case 1. So case 1, so that the way that we're going to write it is that d is going to be all the values of x and y, such that, so y is going to be between two values, and x is going to be between two other values. Okay, this is how you're going to write it. Okay, so now because we're doing it in case 1, so this will be case number 1, we're going to draw an arrow going from the bottom to the top. So remember, this is the region that we're going to use. Now, the top one is really good to kind of know what everything is. So the bottom guy, this guy right here at the bottom, that's your x cubed graph. And then the top one, we're going to call it the green graph, would be your square root of x. So notice that my y values, in this case, because the arrow is going up, we're going in the y direction. So my y values are going to the lowest one, which is x cubed, to the highest one, which is square root of x. So my y values is going to start from x cubed all the way to the square root of x. All right. So that's where this guy's going to be, from y equals x cubed to y equals square root of x. All right. Now, what about my x value? So since I took care of those, this is where I'm going to look at my x values now. So here's my x values. And what exactly is the region where these guys intersect? So you can see that this is going to be from x equals 0 to x equals 1. So my x values are going to go from 0 to 1. So when I set up my integral, right, whatever my function is, I'm going to start my inner integral is going to go from x cubed to square root of x. And then my outer integral is going to go from 0 to 1. All right, so now how do we set it up as case 2? So in case 2, I'm just going to write it this way, same thing, x comma y, such that now my y is going to be between something and something, and my x is going to be between something and something. All right, now because I'm writing in the other way, let me go ahead and erase a couple of things. So let me just get rid of this. Oops, I erased the graph. I'm going to do exactly the same thing. So we know that the bottom graph, the red one, is still the x cubed graph, right? Still y equals x cubed. We know that my top graph is still y equals square root of x. Erase this guy. So now what we're going to be taking a look at is now an arrow going towards the x-axis. So what is x equal to? So x is going to be piercing through the green graph first. But notice, in this case, we want what x equals to. Right now we have what y equals to. So that's really easy. We can just square both sides. You can see that x is going to be equal to y squared. Okay, so it's going to pierce through y squared. And what is the other x value that this is going to pierce to? Well, it's going to be the other side. Well, we can just take the cubed root to both sides. We got that x is going to be equal to the cubed root of y. So it's going to go all the way to the cubed root of y. All right, now because we were looking at the x direction, now we're going to look at the y direction. Where are the two y values where this region is at? You can see that it's going to be from 0 all the way to 1 in the y direction. So this will be from 0 all the way to 1. Okay, so this will be my case 1, and this will be my case 2. So notice both answers, even if you went ahead and did the integral, double integral of whatever function it may be, you can use either or. Both of them will be perfect. It really is just a matter of preference. Just be very careful with which one you want to be able to use, because sometimes it'll depend on what the function looks like in the inside. Sometimes, and also you don't want to mess up the dy and the dx's. All right. So just remember that whatever these variables are in the first integral, if these are x's, then this inner one should be y. If they are y's, ooh, there's a mistake here. There should be a y here. Then this outside should be an x. All right, so in the next video, we will do an example.